Hello everyone, welcome to a new lecture in the series of AI using Python. In this lecture, we will be discussing on Principal Component Analysis or PCA. PCA is a linear dimensionality reduction method which comes under unsupervised learning. In PCA, the training data consists of the input data which we call as the unlabeled data. It consists of n observations of the vectors x1, x2 up to xn, where each xk contains small n number of variables which we can call as the input variables. In PCA, the dimensionality reduction is achieved using a linear transformation where P is the matrix which is used for transforming the input data into a latent space where the input x is transformed into a latent vector y. Y contains small m number of variables and we assume the value of m is less than or equal to n. And here P will be an n by m matrix which transforms the input vector into a latent vector. Then from the latent vector, we can reconstruct the input using the inverse transformation, which gives x hat equal to py. Here, if we substitute for y, we will obtain x hat equal to p into p transpose x. This transformation matrix P is constructed in such a way that it has orthonormal columns. Therefore, P transpose is equivalent to P inverse. In PCA, the objective is to find the optimal transformation P such that the reconstruction error between x and x hat is minimized. This gives the optimization problem for PCA as finding the optimal P which minimizes the reconstruction error, or this is basically equivalent to xk minus xk hat over all the samples subjected to P transpose P equal to Im. This is basically the orthonormal constraint which makes the columns of P as orthonormal. Once this optimization problem is solved, we can obtain the optimal P using which we can transform the input data into a latent vector. And here if m is strictly less than n, we have dimensionality reduction is achieved. And we can use these latent variables as the new features which are lesser in number, which we can later use for various modeling applications. Here we will be illustrating PCA using a numerical example. First, we will be importing all the libraries. Here, we will be using the PCA function from sklearn library for implementing PCA. And the dataset used here will be the same as from the previous lecture. So here the dataset consists of 100 samples, which consists of 10 variables, where we have 4 linear relationships between the variables and also 2 nonlinear relationships. Here we are defining small letter m is equal to 5, which means we are considering the number of latent variables as 5. And here we are normalizing the data using the standard scalar function. This normalization is performed for making the mean of each variable as 0 and the standard deviation as 1. And using the normalized data, we can train the PCA model, where we will be using the PCA function for training the model and give the normalized data or x as the input to the PCA function. Once the model is trained, we can extract the principal component matrix or P matrix using pca.components underscore command. Then using P, we can find the latent variables as the product of the input data and P matrix. And from the latent vectors, we can find the reconstructed input or x hat as y into P. So note that here in this Python example, we have considered the samples as row vectors, whereas in the earlier derivation, where we defined the theory part of PCA, we consider the samples as column vectors. That's why this difference is appearing. Now, once x hat is computed, we can find the mean square error between the input data and reconstruct data using the mean squared error function, which gives the mean square error as 0.01, which is comparatively small. We can also plot the input data versus the reconstructed data to see how well the PCA able to reconstruct the actual data. This figure we have plotted for the input versus reconstructed data for the first variable x1, in which the red color shows the actual data and the green curve shows the reconstructed data. So here we can see that the reconstruction is pretty accurate. So this basically means that just using 5 variables, we were able to reconstruct the actual input. Now, if we change the number of principal components from 5 to 4 and retrain the model, we can see that the reconstruction is somewhat affected. Now, let's say if we change this from 4 to 3. So in this case, we can see that the error is very high, and we can see that the reconstruction will also be not that much good. And let's also try this with the number of components equal to 6 and see the performance. So with 6, the error is very small. If you see the reconstruction error is 0.0006. And if you see the plot, so it's almost perfect. So with 6, we were able to reconstruct the data almost perfectly. With 5, it is somewhat okay. But with 3, the reconstruction is not that much good. This is because of the reason that in the original data, we had 4 linear relationships and 2 non-linear. In the case data containing linear relationships, the PCA can able to achieve dimensionality reduction in a very good way. But for non-linearly related data, the performance of PCA will get affected. So in the case of data which contains large number of nonlinear relationships, we can use nonlinear dimensionality reduction such as autoencoder. This we will be exploring in the next lecture. That leads to the end of this lecture. Thanks for watching.